Good morning. Welcome to the 1.4 warm-up exercises check. We've got these 6 warm-up exercises here, a little more than usual, because 1.4 is a pretty meaty section. So hopefully you've tried these exercises, you have gotten some answers, and you are here to check your answers. So if you haven't done that yet, pause the video right now because in a few seconds all of the answers are going to appear. All right, here are some solutions for exercise 1. Hopefully you got something that looks like this. This is a vector equation, which is saying the same thing as this system of equations. Like this vector on the left is going to equal the vector 4, negative 3, 2, if and only if the first component of the linear combination is 4, and the second component of the linear combination is negative 3, and the third component is 2. So they are saying the same thing. For exercise 2, 3, and 4, hopefully you got C, B, and B. For exercise 2, this was maybe a trickier one if you're not used to visualizing things in 3D. The span of these two vectors is the plane that includes these 3 points that I drew here. And that plane ends up just being the same thing as the x1, x3 plane because it just includes all points basically where x2 is 0. If you're having trouble with my little drawing here, I made a little Desmos graph which might make it easier to see. Here are the 3 points labeled in, well, 0 is part of any span because 0 is a linear combination of any vectors. You can do 0 times 1 plus 0 times the other one. And also here's the v1 and v2. And yeah, the set of all linear combinations of those just looks like this plane, which is the xz plane, also known as the x1, x3 plane, where y is always 0. Okay, for exercise 3 and 4, the answer for these are the same. Like for 3, it's definitely, the span is this whole line here. It includes v1, this point, as well as any multiple of it, which means you can stretch it out as much and get to any other point, shrink it down smaller, multiply it by a negative number, multiply it by 0, all that stuff. So that is the line through 0, 0, and the vector 1, 2. Exercise 4 is the same thing because v2 is equal to 3 times v1. It is on the same line. So including multiples of v2 doesn't change anything. Any linear combination of v1 and v2 is going to be another point somewhere on this line. All right, so with 5 and 6, let's look at those. Here is A3 written as a linear combination of A1 and A2. Notice that this doesn't necessarily always work if you don't know that x3 is not 0, because if x3 is 0, then you're not allowed to multiply by 1 over x3, because that would be division by 0. But in this case, it's okay. 1 over x3 is a number, and you can multiply it by both sides, and you get a3 as a linear combination of a1 and a2. Likewise with exercise 6, we just, to get 0 as a linear combination of these other vectors, we just need to move the a3 over to the left side, subtract a3 from both sides, and this is a linear combination with coefficients y1, y2, and -1, and it gives you 0. So yeah, these last two exercises illustrate an important point, that these two statements are equivalent, that if it's possible to write a3 as a linear combination of the other two vectors, which is like what we have here, then there exists other numbers, x1, x2, and x3, with x3 not equal to 0, that make it so you can write 0 as a linear combination of these three vectors, which is what we've done here. The -1 is not 0, so you just notice that. And likewise, if the second thing is true, if there exists numbers x1, x2, and x3, where x3 is not 0, that make 0 a linear combination of those a1, a2, a3 vectors, then you can do what exercise 5 does and write a3 as a linear combination of a1 and a2. So going from here to here is what exercise 5 was about, and proving this the other way is what exercise 6 was about. So hopefully you got these okay. 1.4 is going to be a meaty section, and we'll dig into it in the next video.